and we can start with one of the most famous philosophers of all time, Ptolemy, who had a go at this. Now what's interesting about this, I'm going to describe his model in a second, is this model was the standard view for over 2,000 years, and it's wrong. It's fundamentally wrong. But the reason why Ptolemy is wrong in part is because we don't have the data. We don't have any way of deciding who's right, who's wrong in their model of the universe. So what does Ptolemy do? Well, Ptolemy wraps a couple of observations and some philosophy together. So the first thing he says is, well, the Earth isn't moving because if it is, we'd all be blown off. And that's actually not an unreasonable thing to suggest. We all know if you walk, you feel a bit of air, if you run, you feel more, and so on. So you could imagine if the Earth is moving around something, then we'd feel it. And we don't. So it can't be moving. That's wrong, but that's a reasonable observation to make in the first instance. He also noticed that you can explain the movement of the planets. So I'm going to come to a problem in a second called retrograde motion. But if you look at the Earth, then let's say Mercury is moving around in its ellipse, Venus is moving around its ellipse, the Sun and so on, in its circle, is moving in its circle. So things are moving in the sky. That explains why planets move. The stars, on the other hand, for no good reason, are here and they don't move. So that explains why the stars don't move except as one big bunch together. So they just all move together as one big bunch, but they're all fixed the same to each other. So this distance between these two stars never changes. So this model actually explains a lot of what you see in the night sky. It explains the planets moving and why they move differently, because Mercury and Venus will move maybe differently to one another, and that's what we see in the sky. The stars all move together. However, there is an immediate alternative, which is that if something like are these and they're moving, but they're very, very far away, then you won't notice them moving so much. So the model isn't foolproof, but it's the model that puts the Earth at the center, and it puts things going in circles. Now, circles mightn't appear as important, but it's going to become very important in a minute or two. So if we go to Ptolemy's model and we look at does it fit the observation. So I think, for those of you who are teachers, if we think about what fundamentally drives science, well, observation ultimately drives it. Now, you might come up with a theory like Einstein, and we've spent the last 100 years proving or disproving Einstein. So if you're really very smart and maybe a little bit lucky in the way you approach things, you might come up with a model that turns out to be right. But mostly, people only pay attention to it if you can prove or disprove it. So if you watch planets in the sky, like this is one of Mars, then it actually comes along. This is taken every sort of 10 nights. It does this, and then there's this really interesting little loop, and then it continues on its way. So this is an observation called retrograde motion. So Ptolemy said, okay, bit of a problem here. I got to explain retrograde motion. So what do I do? Well, something quite smart, actually. That's maybe a little bit difficult to see, but it's worth focusing on this just for a minute, because it shows how you can creatively come up with a solution which actually is still the wrong one. So what Ptolemy said was, the Earth is still at the center, everything is still going in circles, but let's imagine that you have, for example, Mars over here. Actually, let's take Venus because it's actually easier. No, we'll take Mars. Well, it doesn't really matter. So Mars, instead of just going on this big circle here, this outer circle, is going on a smaller circle as it goes around the bigger circle. So if you put Mars on a small circle, then look what happens. It goes left to right, then it comes the other direction. Okay, so sometimes it's going this way, sometimes it's going backwards. That's exactly what we see here. Sometimes it's this way, sometimes it's going backwards, and then it goes on again. So this model works, and everybody's happy. Until you... by the way, one thing, sorry, I forgot, I hate that. The sun is no epicycle. So now you have to throw in something. The sun doesn't have an epicycle. So the stars are fixed for no good reason, and the sun doesn't have an epicycle for no good reason. Why? Because it fits the observations. Now theories where you start to add in little things like that, like it only works on a blue moon of a second Tuesday of the third month in May type of thing, usually isn't a good way of approaching science. So if you put in random things about, we have one model, but it's different for one or two things, that's usually, not always, but usually an indication that there might be a problem with it. Nevertheless, Ptolemy persisted, and in fact so much so that as the observations became more accurate, he realized one epicycle wasn't enough. So what do? You put another epicycle on the epicycle. And that adjusts the movement of the planets just enough so it works. But this is also inherently random. You just keep on adding stuff in until it fits the data. And just to come back to this assumption, for non-scientific reasons, for philosophical reasons, the Greeks believed that circles were a perfect form and that in the universe things should hold a perfect form. So they insisted on things going around in circles, and they insisted for philosophical, partly, but some science reasons like this, you wouldn't get blown off the earth, they said you got to be at the center of the universe. But really, putting us at the center of the universe was really because we're important. That's what really drove that, not the science. It was the philosophical view that somehow we're really important. There's our first lesson about our place in the universe. As soon as you assume that we're really important, you miss the whole point that we're utterly irrelevant in comparison to the universe. Not irrelevant to one another, but as far as the universe is concerned, we're irrelevant. So these models become challenged by better observations. So what do? Well, you hang on to your model for 2,000 years, and then 2,000 years roughly later, so think of that, 2,000 years. So the books are all written and people are making more observations, and for 2,000 years they're afraid to do this, put the sun at the center. If you put the sun at the center of the universe, admittedly, now you still got fixed stars out here, so this guy Nicholas Copernicus decided, okay, we'll leave the fixed stars as they were, let's not go messing with that. But these moving points of light or planets, it would be much easier to describe them if we put the sun at the center. And then the Earth goes around the sun, so the Earth is no longer the center of the universe. Philosophically, this is the big leap. Once you've done this once, everything else is actually relatively straightforward. Because in a way it doesn't matter whether you're here, or whether you go in a circle or a square or something like that. The key point, the key philosophical difference is you no longer have to be the center of the universe. And if you do that, and this is, maybe for tonight I won't go too much because I know not everybody in here is teaching, but if you look at it, this model actually predicts retrograde motion more naturally. I'll just give you an example. So here's the Earth going around, and here is, say, Mars going around. So Mars is going around a bit more slowly. So if you look from the Earth to Mars, it appears to be here. The Earth continues around, Mars has moved a bit, so now Mars appears to be here. The Earth continues around, now Mars is here. But now as the Earth overtakes Mars, Mars appears to go backwards, and it naturally gives you this little loop. So by simply doing this, no epicycles required. Now there's a thing called Occam's razor. I don't know how many of you have heard of Occam's razor. I always like this. I learned this years ago. And Occam's razor says this: if two theories equally well explain a given phenomenon, and one theory is simpler than the other, then the simpler one is most likely to be the correct one. So I said again, if two theories equally explain something, but one theory is simple and one is complicated, it seems that our universe for the most part chooses the simpler theory. So this is a much simpler model. And Occam's razor, it's not a proof by the way, it would suggest that this is more likely to be the case. So Copernicus said, this sorts out your issues much simpler, and he got into all sorts of trouble with the church over that. That's not maybe for tonight's discussion. It did open up the question of why, but I'm happy to chat about it afterwards in a way, but it did open up the question of why aren't we blown off the Earth? That still wasn't clear. Why aren't we blown off the Earth? If we're barreling around the sun at who knows what speed, why don't we get blown off? This didn't address that particular issue. So people who objected to Copernicus's model chose this as the issue, and they said epicycles is okay because this is a bigger problem. And that's actually that's not completely invalid. You know, if you say, well, you've got two problems here, epicycles or blown off. I know we're not being blown off for sure, so we mustn't be moving. It's not a complete mad suggestion to have.